Our second speaker, Dr. Andrew Prentice, is a bit of a legend amongst Monash students, staff and far beyond. Andrew began his study here in Melbourne before heading to Oxford to complete his PhD on a prestigious scholarship from the Royal Commission of the Exhibition of 1851. After a short period in the US, he began a lectureship in applied mathematics at Monash University in 1972. And in fact, he actually taught Peter Betts, our last speaker. He's been here ever since, although he technically retired in 2010. Andrew is a particularly popular lecturer, and he won the Vice-Chancellor's Award for Teaching Excellence in 2011. There is also a rather large group on Facebook called the Dr. Andrew Prentice Appreciation Society, which I'm not sure if he knows about. Outside Monash, Andrew enjoys bushwalking, swimming, and has developed a recent interest in working out how to grow roses the best way. In his retirement, his wife has sent him on a cooking course, but he's been a little bit worried by some of the course titles like Home Alone Cooking and Cooking for One. But she assures him that his best interests are at heart. On the research front, over the past 40 years, Dr. Prentice has developed a radical new theory of how our solar system was formed. Predictions from this theory have proven impressively correct time after time as probes have been sent out to each of the planets to collect data. But I'll leave Andrew to fill you in on the details of this rather interesting story.
I joined the maths department in 1972, and Michael Deacon joined it a few years earlier, and I mention him now because very sadly, through ill health, he passed away a couple of weeks ago, and he was a very, well, Peter probably remembers, a very fine lecturer in applied maths and edited Function magazine, so it was very sad that he went so early on. Now, coming to the younger generation of maths, you may have seen in the news last week that this Iranian girl, Mariam Mirzakhani, won the equivalent of the Nobel Prize. It's called the Fields Medal in mathematics. It's an amazing achievement, and you have to be under 40 for that, so I miss out probably by nearly a factor of 2. Now, coming to our solar system, which is even older again, as Peter pointed out, no way it can enter a fields competition. I'm going to talk a little bit about some of the planets within it and maybe how the solar system formed, and do a little time check. Is it saying 1:30? Yes, that's important. So here is the solar system we knew until about 20 years ago, and no, out as far as Pluto, which had been discovered in about 1930, and the sun dominates the whole thing. You know, it's many times more massive than the Earth. But in 1992, I think they found the first of these Kuiper belt objects called Smiley. It's not shown there, and I should quickly point out the words Kuiper belt are not emblazoned on that. I know Peter referred to the Almighty a moment ago, but even this was none of his doing. This is an artist's rendition, but it shows Pluto probably came from there. And beyond the Pluto, you go out to the orbit, what's called the Oort cloud. That's where comets come from, way out in the boondocks. And but when in 1992 they found Smiley and a few others, and more recently many others. And a lot of them have got moons too. So it looks like moon formation is quite common amongst these objects. And in the last few years, they've found more moons, Nix and Hydra, and last year a couple more as well, Kerberos and Hydra. And I'd forgotten about 20 years ago when they found the first few of them. I did actually make a paper, presented a paper to the American Astronomical Society about how Pluto would have formed, and did suggest, as you can see on the right-hand side in red, thanks due to my very fine Steve Morton, who I think is here today. He's marvellous what he can do, tricks like that. And anyway, I also wrote another paper in the Australian Journal of Astronomy suggesting that Charon had actually spun off from Pluto. Pluto once, when it formed, somehow or other its mantle had become liquid and it was spinning very rapidly, perhaps through the what are called short-lived nuclides. All the rock had settled to the centre, and it had spun off. Pluto had been spun off, and there would have been many other bodies beyond that as well. Here's a sort of graphic that was produced by a fellow Wolfson. So this is called the Fission Origin, and I'm hoping in about next year, July, they'll be able to test that theory, because if this model is right, The fission theory suggests the moons of Pluto should be made just of ice. These are the blokes at the bottom of this graphic. Whereas if Pluto had formed by an impact, it would have rock and ice. So that'll be a challenge for next year, and I'm working out some models for those moons. And so the new solar system looks like this, where we include the dwarf planets, and also you notice Ceres appearing there. That's that in fact is the largest asteroid. It's a bit of a mystery object because it's very much less dense than the other asteroids around it. Most of them are quite stony, like Vesta on the right. And yet if they all formed in the same part of the solar system, why are they so different? And so most of the planets, like the inner planets, are very rocky, and there's a very steady gradation of density from Mercury, which is mostly iron, down to Ceres, which I mentioned a moment ago. It's probably 75% rock and 25% water. But there is a steady gradation which does suggest the planets more or less formed in situ where they are, and then maybe there was a temperature gradient running right through the system. And that's little Mercury, a mystery planet. It's actually similar to what Peter said, like the Earth. It does have an iron core, much bigger than the Earth's core, iron and nickel making up 75%, much more than the Earth's core of only 32. So that's a mystery. How did that happen? Some guys, and I think that they're a little bit disillusioned, are suggesting Mercury became iron-rich through giant impact. Oh, it's shocking. And it once had a rocky mantle which got blasted off, leaving Mercury greatly iron-rich. But this would be a very fierce event, and the same model has been proposed for the Earth's moon. The giant impact, it's here, there, it's everywhere. And I think it's terrible. But such a scenario for the formation of moon would have made the moon devoid of volatiles, and yet that's not true. When Neil Armstrong stepped down on the moon 45 years ago pretty well, and a month, and that's Buzz too, but Neil's reflection is in that helmet there. If you move in closely, you'll see young Neil. And there's another bloke called Jack Schmitt. He was on one of the last of the missions, and he went around collecting samples. And holy mackerel, some of the samples weren't analysed till many years later, and these are called glasses, and they discovered that really the early moon was quite rich in water. And it does suggest, in fact, the moon and the Earth are very similar in composition. They probably formed in the same part of the planetary system. It does move us away from the giant impact model. And for Mercury as well, they discovered there was almost as much uranium relative to thorium as there is on the Earth and in other planets, and had Mercury formed through a giant impact, all of the uranium would have boiled away. And Sean Solomon talked about that 3 or 4 years ago at the AGU. I guess Peter's a member of that. But he says the giant impact models don't seem to be able to explain that, and no model could explain the moment of inertia and the mantle inertia, and that included me at the time. But when I went back and had a look at my model, I was only dismissed by a whisker, because I didn't know he was going to plant that slide. It was a bit slimy because I was the next speaker. This is at the AGU. But I discovered later on my moment of inertia factor was just outside at the bottom right, but only by 1.19 sigma, which is not much statistically, and my mantle moment of inertia was well inside. So I think that iron model I had was unfairly dismissed. Well, how did the planets form? In about 3 minutes, at least that's the duration before Kay will start to get stand up and get fierce, though I've never seen her in a fierce mode before, so that would be exciting. Here's Laplace. He was suggested the modern Laplacian theory, and during the last 40 years at Monash, I've been creating a modern version of that. And I got the impetus for it from my mentor at Oxford, Dirk Tahar, who said I should include turbulence in the model. And what I have done, tried a long time to do it, but I included, as well as gas pressure, turbulent pressure, which would greatly extend the outer layers of the cloud and give the early sun a very centrally condensed appearance. A bit hard to explain that now, but the outer layers would be pushed outwards. The moment of inertia would decline dramatically, to about 0.01, and there'd be a dense shell at the surface, and a very dense shell of material, and when you put rotation in, it would slip down to a belt. And then when you followed it inwards, and this is another movie that Steve helped me with, you're looking at the early sun way out, contracting in from the orbit of Neptune, shrinking and becoming steadily more, rotating more, bulging out and shedding a ring of gas, just as Laplace had suggested, a ring at the orbit of Neptune and Uranus and Jupiter and Saturn, till you had this family of gas rings, and that's a resurrection or a rejuvenation of that model. And I've had students look at that and improve that movie. And with gas rings, the nice thing about gas rings is that the gas causes focusing of the little solids. When they cool down, all the solids focus onto the mean orbit of the gas ring. And when the gas rings, the slurry is sufficiently compressed, then you have a nice situation where the rocks accumulate to form a planet. And there's very little radial movement. And the outer planets form ahead of the inner planets, and Jupiter formed ahead of the asteroids. The asteroids would have really loved to form a planet, but Jupiter was a villain and stirred them up. And they never got a chance, not even to order a Big Mac. It was shocking. Now, I've had a lot of trouble over the years, but in 1972, my first paper was sent in, and unfortunately it was shot down by the Royal Astronomical Society, and I know myself to America. It fell into the hands of Big Al, Al Cameron, and he said, when it became apparent that Prentice was using supersonic turbulence, I quit. Do not recommend a paper publication. I cannot recommend the law. So this was not encouraging. Oh, he's a naughty fellow. That was called Big Al. He's a very naughty man. Now, I got fierce about that, like Kay will be in a minute. And I made many planetary predictions about what would be found out. And that's what Kay was talking about. One of the most important ones was Bode's law, which relates the mass of the orbits of the planets to the mass of the ring over the parent and the moment of inertia. Because F is so tiny, the Sun can divest of its original spin angular momentum at the expense of losing very little mass. And that's what explains why the planets are so small in mass compared to the Sun. And the Voyager tour that went first past Jupiter and then Saturn, and then on to Uranus and Neptune, and it was a field day. It allowed me to use the modern Laplacian model to make predictions exactly 25 years ago, within a few minutes, of the possibility of some moons existing between Neptune and Triton, which is right down at the bottom. I had a lot of trouble getting it published. Eventually published in Japan, and they made a nice graphic here. The only symbol I really understood was the very last one at the top on the banner, which is a bit of a worry. It's a question mark. I was wondering, is this all crap? Anyway, I hope it wasn't. But holy mackerel, within a few minutes, they found those 4 moons doing exactly what they did. And then I've also been interested in Saturn, and there's that villain called Titan. Oh, he towers over the rest because he's an interloper, a very naughty fellow. He formed outside the system and was then captured, discovered by Christian Huygens, and that's what the probe's named after. But you can see there Titan is so big, and I realized that in 1980 when I was visiting the Jet Propulsion Lab and wrote a paper about it, that Titan is a captured body. Its mass was far too big, and I predicted there, and it was a paper I published almost 35 years ago. And Titan came in, it destroyed some of those native moons. There was a moon at 17 that's no longer there, and Iapetus had a very nasty skirmish with Titan, and you can see it was left spinning like a top, and you can see a little ridge left there, a bit like myself, an equatorial ridge. And then the Sweeney spacecraft, oh yes, it got there 10 years ago. It looked at Titan, its atmosphere. It's a stolen atmosphere. It's made up of the ices of the lost moons, ammonia and methane. And had Titan formed in a natural orbit of Saturn, it would have an egg-like appearance, like this. But it doesn't. It looks more like tomato or spinning. It's an oblate spheroid. And that's exactly what they seem to have found, that Titan's moon is slightly oblate. It must have come from outside that system. And there's a picture of me with Zebka, who made that discovery there. I'm obviously encouraging him to look at my poster, but he's facing the wrong way. And, oh, it's shocking, Kay. It really is bad. We've seen that one? No, that's a newie. That's the temperature gradient. You can compute the temperatures of these objects, and that's exciting too. Recently I worked on Ceres. There's a temperature of 267. But you can explain the chemical condensation of the solar system. And this is another graphic Steve put together. Steve Morton, by the way, is in the middle with the camera there. And it fits the densities and explains Mercury. And the last challenge I have is Ceres, because why isn't it like Vesta? Vesta's mostly rock, and it does fit in with my model. But the real challenge for me, and I've got to come clean, Ceres is very, very different from Vesta. They should be the same. They form from the same gas ring. And I'm going to be putting a paper into the American Astronomical Society tomorrow night for their DPS meeting in Arizona. And I think I've worked out what's going on. It's tied up with the fact that Ceres had a lot of water of hydration in its interior. It probably had a lot of brucite in the beginning, and brucite's water laden, and I think a lot of Ceres water has come from that. But we must leave that Saturn system and the Ceres and enter, and also I must stop here immediately. Thank you very much, Kay.